This is why they use the Henderson-Hasselbalch in this, because it's very close to the pKa. So what we can do is we can figure it out using the shortcut method here. The shortcut method is this. Since this is the buffer region 1, the pH is going to equal the pKa plus the log of the base over acid ratio. And so the pH that we want is 385, and the pKa is 474 equals the log, and then we can figure out what the ratio is, and then go from there. 0.13. All right. And so if we have a base to acid ratio of 0.13, then this is 0.13 over 1. And so the way you would read this is 0.13 parts of base to 1 part of acid. And so that means we have 1 part of unreacted acid and 0.13 parts of that were converted into base. And so what we need to do is we need to figure out the total parts here. The total parts would be just 1 plus 0.13, which gives us 1.13. And then we figure out the ratio based on that. 0.13 out of the total, 1.13, was converted into base. And then that leaves 1 part out of 1.13 unreacted acid. And so this would be the percent reaction, or the equivalence point. It would be the 0.13 out of 1.3. And so, in other words, to neutralize all the parts, this would be 1.13. But we've only neutralized, it's going to be closer over here, we've only neutralized 0.13 out of them. So we've only gone 0.13 out of 1.13. And so, looking at this, if we have 25 milliliters of acetic acid and our base is twice as concentrated, then we're going to need half as much base to neutralize that acid. And so to hit the equivalence point is going to take 12.5 milliliters. And so what we do is we set up a ratio like this. X milliliters over 12.5 is equal to 0.13 parts out of a total of 1.13 parts. And so I could do that like this. 0.13 out of 1.13 total is equal to x out of 12.5. And then solve for x. Well, what I've been doing is I've just been saying, well, you know, it's going to be 0.13 out of 1.13 under 12.5 milliliters. And so this is the equivalence point. So if we're at the half equivalence point, it'd be 1/2 of 12.5. If we're at the 3/4 equivalence point, it'd be 3/4 of 12.5 milliliters.
What if the numbers aren't so clean, like 0.375 and 0.281? How would you know? How would you know the volume attachment to reach the equivalence point?
Well, these numbers aren't clean here. You know, this is not like the half equivalence point or the 3/4 equivalence point. This is a 0.13 out of 1.13 equivalence point. It doesn't matter what the numbers are. You know, you could have 387 parts total, you know, and you're, 5 parts out of the way. You know. Numbers don't have to be clean. It's just some ratio, just some fraction of the total. And the fractions, you know, when you're looking at it, like if you look at the fractions just on a ruler, you know. On a ruler, we say, okay, this is 1 inch, or it's 8 out of 8 inches, or it's 16 out of 16 inches, or it's 32 out of 32 inches. Or it could be 105.638 out of 105.638 inches, right? It doesn't. We could just make this not, rather than a whole number, we could just make it whatever, parts we want. And that's what we're going to get, because this, the fractions, when you have something like this, we don't have, well, a nice clean number each time. Sometimes it's between those. So, but anyway, that's what it comes out to.
Can you explain again how you got, or how you need that 12.5 milliliters?
How I did that? Okay. I did the calculation just in my head, but the thing is, to hit the first equivalence point, that means we have to have an equivalent amounts of base and acid. And so I know how much acid I have because it's fixed. And so what you could do is you could just do a stoichiometry problem. 25.00 milliliters of HAC, and then we can convert it into liters. And then we know the molarity. It's 0.100 moles.
So it doesn't matter if it's a strong acid or a weak acid?
No, it's just, yeah, it doesn't matter because stoichiometrically it's going to take the same amount whether it's strong or weak. If it's diprotic, it depends. If you want to go to the first equivalence point, then it takes one equivalent of sodium hydroxide. If you want to get to the second equivalence point, it takes two equivalents of sodium hydroxide. So it'd be 2 sodium hydroxide to 1 mole of acid ratio. And so if this were diprotic and we wanted to hit the second equivalence point, then it'd be 25 milliliters. We'd end up, right, because we just continue this on. The difference would be in the mole ratio here. Right now, it's just the first equivalence point, 1 mole of sodium hydroxide to 1 mole of acid. This is what it means to be at the equivalence point. We have equal amounts of acid and base.
Right. You should show the switching it to 200.
Oh yeah. Then we're going to go over here. It's going to be 0.200 moles of sodium hydroxide for every liter. So we end up needing only half as much, and then convert it to milliliters. What it comes out to. And so I do that to figure out the volume. And so we would have to do stoichiometry calculations. I just picked the numbers so we could do the stoichiometry calculation easily because they were equal molar, and so they'd be equal volume, But the book doesn't do that. And on exams and homework problems, you aren't going to see that. This is a 0.100 to 0.200. There's that other problem, with the weird concentrations, 0.385 or whatever, 0.190. And so that you can't do in your head so easily. You'd actually have to sit there and punch it out in your calculator to figure out the volume, the equivalent volumes. And all it's asking is, if you have, let's say I have 3/4 of a mole of acid, how much base, sodium hydroxide, do I need to get 3/4 of a mole? Well, it depends on the concentration. The concentration will tell you. Okay. Other questions?
Number 57 or 58.
Okay, number 58. Okay, can you read out that problem because I don't have it and I didn't bring my book. The endpoint, is the endpoint the same as the equivalence point? No. The endpoint's is where the indicator changes color.
Oh, no, sorry, number 59. Okay, what stoichiometric concentration of the indicated substance is required to obtain an aqueous solution with the pH value shown of A, barium hydroxide for pH 11.88.
They're asking what concentration we need? What concentration? Yep. Okay. if you have 1 molar acetic acid or 0.100 molar acetic acid, you know, does that mean you have 0.100 moles of acetic acid molecules per liter and nothing else? No, that 0.100 is the total. You know, if you were to take all the species and then just combine them so that they would form acetic acid, then that would be the total. And so when somebody is asking you, what is the concentration of barium hydroxide to get this pH, are they asking about the initial barium hydroxide or the equilibrium barium hydroxide?
Equilibrium.
So if you see a bottle or beaker that's labeled 0.100 molar acetic acid, is that the initial acetic acid or is that the equilibrium acetic acid concentration?
Initial.
This is the initial. In other words, this is the total acetic acid concentration. You know, and what's going to happen is some of the acetic acid is going to just stay as is, but some of it's going to break apart into hydronium and acetate. But when we combine this plus this, we get 0.100 molar, right? There's a total concentration of 0.100 molar. And so in other words, we wouldn't call this 0.991 whatever molar acetic acid and 0.1 molar or whatever, you know, 0.001 molar. You know, and so we're looking at just the total concentration. This is what we mean by total concentration. And all the bottles are like this. You know, all the bottles aren't telling you what the equilibrium, they're just telling you, you know, you took this many grams and mixed it in there. However it splits apart is how it's going to split apart, you know. That means, like, you know, for people who are, people who know about this, they'll go, okay, if you take some sodium phosphate and put it in water, does it stay as sodium phosphate? No. You know, sodium phosphate's a pretty decent base. It's going to hydrolyze water to form a monohydrogen phosphate and dihydrogen phosphate and maybe a tiny bit of phosphoric acid. And so when people think about chemical reactivity, you know, and somebody says, well, you know what, I don't have any sodium phosphate. I have some sodium monohydrogen phosphate. You know, is there going to be a big difference in the reactivity between those in water? No. And so if I'm going to precipitate something with phosphate, I can precipitate it with sodium monohydrogen phosphate, no problem. It's going to do the same thing, essentially.
How come?
There's a species.
How do you know?
It's sodium phosphate in water is mostly monohydrogen phosphate. I mean, once you put it in water, it changes into monohydrogen phosphate anyway. And then hopefully the precipitating, whatever it's precipitating out with, knock off the hydrogen easily, precipitate it out. You know. In fact, when we look at these things, we look at speciation diagrams. The pH is going to be different because this is going to be more basic than this. So the pH is going to be different. And so we look at the species. If you put phosphate in water, it depends on the pH of the water. You know, and so if you look at the population of species, you know, it varies. Like, for example, at very low pHs, you know, there's not much phosphate. Maybe it's all phosphoric acid at very low pHs. But at very high pHs, it's pretty much, you know, all phosphate. And so we have speciation diagrams. Depending on what pH you have, you can see what species are dominant. This is like you do an ice calculation, right? And figure out what the concentrations are at equilibrium. But this is what we do. We just map it out according to pH. And so just because it's phosphate, yeah, it's phosphate I put in water, but you know, if I have 0.100 molar sodium phosphate, oh, it's not all phosphate. I got a whole bunch of other species present. And so it's something we think about, but when we're trying to say, okay, I need some 0.100 molar sodium phosphate, you aren't going to tell them, well, how much monohydrogen, how much dihydrogen, right? It's just, and then you got to figure out, oh, what pH do I need to get that ratio? You know, it would be too much. So we just say that's 0.100 molar sodium phosphate, and who cares what it splits up into right now, because it'd just be too much of a headache to keep track of all that stuff. And so the same thing with this. You know, when somebody asks you, you know, we got a pH of 1188, you know, how much barium hydroxide do I need to mix in there? You know, they're talking about what is the initial concentration of barium hydroxide you got to put in there to get this at the end, you know, at the equilibrium. And so we work backwards, right? And so working backwards is the same thing. Except, are we mixing anything? No, they just want the initial. And so we don't have to do the solution dilution. We just start off with the equation. So barium hydroxide is what we call a strong base. This, right? Although you don't have to do it this way. The book's not going to do it this way because this is a long way of doing it. And so we're going to say all the hydroxide comes from barium hydroxide and negligible comes from what?
Water.
Water. And so we get the pH, we convert it into the POH, which gives us the hydroxide ion concentration. This is the hydroxide ion concentration at equilibrium. We plug it in here. What we're solving for is barium hydroxide initial here. This is going to be 0, this is going to be 0. But we know something, barium hydroxide, well, this is what we call a strong base, right?
100% ionizes.
Strong base is 100% ionized? No, strong base is, no, we call this the soluble salt. This is soluble salt. Soluble salts are strong electrolytes. This is the strong base here. Right? And so soluble salts ionize 100%. So barium is going to ionize 100% too. Yeah, so this is going to go down to 0. And so the hydroxide ion concentration is going to be the same as 2 times the barium hydroxide concentration. And so the barium hydroxide concentration initial will be half the hydroxide concentration, right? Because this is going to be +2 + 1. This is going to be -1.
-1?
Yeah. Well, I mean,
Why did 2 times
because the coefficients, 1, 1, 2. In other words, this is -1x plus, actually we don't say 1, -x plus x plus 2x.
Okay, there you go.
Okay, and then we would have it. All right, any other questions? No other questions? Okay. Today we're going to do 2 runs of kinetics experiment. You know, in run 1, we're going to mix up some, you know, both of them are going to be the same reaction, but we're going to do it at different hydroxide concentration. And so the first one will just be CbCl plus sodium hydroxide yields CbOH plus NaCl. And so we'll just mix up the solutions. And this run, what we're going to do is we're going to take 10 milliliters of the standard 10.00 milliliters. So we use a pipette to get this kind of precision. Because, you know, we'd either have to use a burette or a pipette. With a grad cylinder, actually grad cylinder, 10 milliliter grad cylinder should give us this amount of precision, but we'll just use a pipette because a pipette's easier. Does everybody remember how to use pipettes?
Squeeze for it.
Do you blow out that last little tiny drop that's left in there? No, this has been calibrated in there. And before you use the pipette, you make sure you rinse it with water and rinse it with some of this solution, which we discard. You know, this is just... All right, and then the sodium hydroxide. In run 1, we're going to use 5.00 milliliters of sodium hydroxide. Yes, I don't know if we have a pipette. We'll probably have to use a more pipette for this one. We might have a 5 milliliter volumetric pipette. Plus, in this case, we're going to add, I'm going to make this experiment quicker, I think. Well, it depends. We'll just leave it. We're going to add 15.00 milliliters of water, DI water. So altogether we'll have 30 milliliters. You'll mix this in a small beaker. Will a cuvette hold 30 milliliters? No. And so we need extra reaction mixture because we always rinse the cuvette. You know, the final rinse is going to be with mixture, so we need to discard some. So this is going to be way more than enough here. And so it's a total of 30 milliliters. A cuvette holds like 5 milliliters. Oh, it goes to waste. We mix that, and then we put that into the cuvette. But you know, at the time of mixing, we should start the clock, shouldn't we? Yeah. Start the clock. The weird thing is, though, that our LabQuest system has an internal clock. And the internal clock on the LabQuest and our clock, the stopwatch, are going to be out of sync. And so we have to see, you know, in other words, when we start the LabQuest experiment, we have to sync it with this clock, you know. And so what we'll do is, you know, we'll take data at regular intervals. And so we figure out, yeah, maybe it's going to take a minute or so to do this. So maybe at minute 1, we'll sync it with the LabQuest, or, you know, it depends on how long it takes you to do this. But you keep an eye on it and then try to sync the 2 clocks, and we'll see what happens. All right, so we mix it, and then we put it into a cuvette. The cuvettes are going to be not round, but square, like this. So we need to fill up the cuvette to a height, you know, near the top, where the light path will go through the solution. And then we're going to measure it. And so we'll go through the setup together. All right, what we're going to see is we're going to see the absorption of yellow-green light, and it's going to be relatively high at the beginning. And we're going to monitor this with time. And so we'll get our first reading there once we start the experiment, and then we'll watch it, how it decreases, like this at regular intervals. And then what we're going to see is that it's going to decrease in a nonlinear fashion, like this. And so the reaction is, what we say, is fast initially because we're consuming crystal violet rapidly, because the concentration drops at a fairly steep rate. And then as time passes, it kind of flattens out and slows down. And so it just gets slower and slower reaction. And so what we want is, well, this is, a graphical depiction of the reaction of crystal violet with time. And so how would you describe this reaction? Well, you might say, yeah, it starts off fast, right? Starts off fast and then slows down. But is that the most?
As concentration changes, the reaction happens slower.
As the concentration goes down, the reaction slows down. Right? It could be logarithmic. And so there are different ways that we could describe this here. And so these are the ways that we're going to describe it. For example, if somebody says, as the concentration goes down, the rate slows down, somebody might ask, well, if the concentration gets cut in half, what happens to the rate? Does the rate get cut in half also? Or does the rate get cut by a quarter? Or does the rate get cut by an eighth? Or what happens to the rate?
It's been discovered that the rate is quadrupled.
The rate will quadruple?
Yes.
For certain reactions it might, but for this reaction, does that happen for every reaction? Does the rate always quadruple? Well, in this case, the rate is actually not going to quadruple, but the rate might get cut by a quarter, Or if the concentration gets cut in half, what happens to that descent, right? And so that's one thing that people look at, they think. Because if they're saying that the rate is going to depend on the concentration, what if I double the concentration? If I double the concentration, will the rate happen twice as fast? 4 times as fast? 8 times as what's going to happen? And so this is what we're going to do. We're going to analyze these things like empirically and see what kind of information we can extract, or what kind of patterns. These are all patterns, right? What kind of patterns we can see in this, and there are lots of patterns. Like, for example, in order to consume half of it, it might take this much time. And so if I consume the next half of it, will it take the same amount of time? Will it take twice as long? Will it take half as long? These are the types of things we want to be able to see when we look at a graph like this, right? And so the first thing we do is we look at the rate of reaction. And so this is going to be the absorbance, which is going to be related to the concentration of the crystal violet. And so really what we're going to do is we're going to convert the absorbance into concentration of crystal violet plus. And so we're going to see how this changes. So in terms of rate, the rate, we have 2 types of rates that we get from this graph. We have the delta CV plus, the change in the crystal violet concentration with respect to time, delta T. Delta CV plus over delta T. We call this the average rate, And so I pick some time interval here, and then I just look at the average rate. Let's say I want the time interval from, time 0 to this time here. And so the average rate is just going to be the slope, the delta T here, the delta CV here over the delta T. This is what we call the average rate. And so over this time interval, I had an average rate of whatever this slope is here, right? And then we have something called the, I'm just making this very broad. I'm not going to get into the details of this. But if we make the delta, very, very small, and so we'll use D instead of delta. And then we're going to put dCV plus over dt. we tighten up this delta t so small that that what we're going to get is the tangent line here rather than what I've drawn here. Let's say I'm interested in the rate at this time here. And so I just want the rate at that specific time, not over a big time range like this. And so at time t. Here. Then this gives me what we call the instantaneous rate. This rate. Instantaneous rate, the way we're going to analyze it is it'll be the slope of the tangent line here. Dt or delta t over, delta CV plus over delta t. All right. Is that enough for this? An explanation? And so what I can have is I can have the instantaneous rate. The instantaneous rate would just follow the tangent line to the curve. And it'll just tell me the rate at any instant of time. Versus the average rate, which we're looking at two points. The instantaneous rate and the average rate are the same if this delta t is extremely small. All right, so we have that, and then the other things we look for is, okay, how does the rate depend on the concentration? Because we see that the slope does depend on the concentration, right? And so that rate dependence on the concentration, rate is equal to this. Empirically, it's been determined that the rate is going to equal something called K, which is called our rate constant, or just a constant, times the concentration, right? In this case, it'd be the concentration of Cv plus raised to some power, which we'll call m. And so what we try to do is we try to figure out this. If the concentration doubles, what happens to our rate? And so if we look here, let's go to half the concentration. We go here, and the rate is going to be given by the slope, how steep it's descending here. And then we double that concentration. So we'll back up here and go to twice that concentration. What just happened to the slope? Did the slope also double? That'll tell us something about the curve. If the slope, oops, so what am I doing here? Yeah, here. The rate is the slope, I should say. The slopes. If I back up here and go twice the concentration and the rate doubled, then m is 1. That is, it's just directly proportional. However, if I go to half the concentration here and I back up and double that concentration and the rate quadruples, then it's a non-linear dependence. In other words, if I double the concentration here and the rate quadruples, then m must be 2 because it's got to be a squared dependence, right? If I double the concentration and the rate goes up by 9-fold, then m must be 3. Okay, the m equals 3 is a bit unusual. Or if I double the concentration and nothing happens, the rate stays the same, then m must be 0. There are some reactions that are just that show a constant rate all the way till the end of the reaction. Okay. And so this dependence on the slope, with concentration, we give names to. So rather than saying, oh, that's what happens, and we call those, like, if m is 0, we call it 0 order decay, or 0 order. If m is equal to 1, then it's just showing how the slope changes, right? Then we call it first order kinetics. If m is equal to 2, we call it second order kinetics. And it doesn't have to be 0, 1, 2. We could have -1. That is, for example, as the concentration goes down, the rate speeds up. We could have things like that happen as well. But these are just ways of describing the differences in curves here, because not all the curves are going to look exactly the same. Now, once we have the data like this, you know, what we'd like to do is fit this to a mathematical equation. We do this because we want to describe this using some, you know, mathematical equation. And so how would you describe a curve? Well, we could describe it using, you know, logs or whatever else, right? Depends on how it fits. Well, there are three patterns that are fairly common that we can describe the mathematics for the curve without too much difficulty. There are actually more, but there are three that you should know. Three common, I guess, graphs or patterns. Let me see. It's when we're looking at the concentration and the rate just doesn't change. You know, the rate just stays constant all the way through. This is called linear kinetics. In other words, if I'm looking at how the slope changes with concentration, the slope here, which is the rate, is going to change with the concentration with some constant, times the concentration, you know, to the m power here. Well, if I double the concentration or if I cut the concentration in half, the rate doesn't change at all. So that means m must be 0. And so this is what we call zero order kinetics here, or zero order in this concentration. The math of this is pretty easy because to describe this line is just y equals mx plus b. And so on the x-axis we have time, on the y-axis we have concentration. So this says the concentration at time t is equal to m, the slope. That slope is delta concentration over delta t. X is time, plus b is the intercept. So the intercept is the concentration at time 0, which is here. And so we can describe the kinetics of this. That is, we can describe this reaction by just the concentration at time t. In other words, with this equation, we can make predictions. We can predict how long it will take to hit a certain concentration. Or if we're at a certain concentration, we can figure out what time it is. And so this is what we want. We want some kind of mathematical equation to describe how this reacts so that the next time we do this reaction, we can predict how long it's going to take, right? If you know the mathematics, you can kind of plan out your experiment accordingly. But we can go on to the next common pattern. The next common pattern we could recognize because it does something funny. If we cut the concentration in half, it takes a time interval, t. Okay, now we start at this concentration, which is half the original, and cut that one in half. And so if we keep cutting the concentration by half, it turns out it takes the same time interval. We call this the half-life. And so to cut the concentration in half, the time it takes is t1 half, or the half-life. And so each time we cut that concentration in half, it takes the same time interval, t1 half. And so the total time here
Same.
would be, yeah, 1 t1 half, 2 t1 halves, 3 t1 halves, etc. And so it's going to fit this kind of pattern like this. Okay, we know that the rate is equal to K times the concentration to the m power. And so when we look at the slope, this is what's going to happen with the slope. In order for us to see this kind of pattern, the slope has to be cut in half each time. Each time we cut the concentration in half, the slope gets cut in half. Here. So in other words, this is M must be 1, because if we cut the concentration in half, the rate gets cut in half. And therefore, this is what we call first order. First order, because of the way it behaves. Now, how do we describe this equation here? Because the slope is always changing, continuously changing. And so if I wanted to figure it out, for example, here, I know my rate. My rate is equal to delta concentration over delta T, which is equal to K times the concentration of M. And so let's say I wanted to figure out how long it takes. Well, if I want to figure out how long it takes, then I just solve this equation for delta T, right? And then plug in my final concentration and my initial concentration. Delta concentration is final minus initial, right? And so let's say I want to know how long it takes to consume 3/4 of it. And so how long will it take to consume 3/4 of my initial? And so the example would be, how long does it take to consume 3/4 the initial concentration, which I'll just write as 0 or I for initial. Okay, so that means if I consume 3/4, how much do I have at the end? 1/4. So I'm going to have 1/4 of my initial original. That's the final, and the original was this, right? And so this would be my delta concentration. And then I'm solving for delta T. But does somebody see a problem with that? Mathematically, it seems to be okay. I'll just plug this in. This is going to be minus 3/4 of my initial. So it depends on where I start, initial. Let's say my initial were 1 molar. So, well, it's easy because delta T is equal to what is it equal to? Delta concentration over K concentration. M was got to be 1, so concentration, something like this, and then solve for that. There's a problem with this. You know what the problem
is to the concentration on the bottom there, that little number by your finger?
This K?
No, the other one, up on the superscript of that same line.
Subscript? This stuff?
The same thing you're pointing out with the K, with the superscript, right by the pen. What is that number? Yeah.
1.
Okay.
We'll just take it on that. It's 1 because each time I change the concentration.
Right.
Okay, this is all wrong.
Why?
Basically. This is all wrong because I can't use this equation. We can't use this equation. The only thing we can say is that the rate is equal to this, but we can't use this for calculations. And so we can't use this equation for delta concentration or delta T. In other words, we can't use it to calculate the times or concentrations. We can't use this equation for delta T or delta T Therefore, we can't use this equation to calculate T or concentration, times or concentration. You know, whereas over here we could, because do you see the rate over here is delta concentration over delta T. And this is, M is 0 here, and so it's going to, K is going to equal delta concentration over delta T. And so in other words, delta concentration is equal to K delta T. Delta T is the time interval. You know, if we start at time 0. And so this is T final minus T0. T0 is 0, so this is just this final time. And delta concentration is the concentration final minus the concentration initial. And therefore, the concentration final is equal to KT plus the concentration initial. K is the slope. See that? Which is delta concentration over delta T. But we can't use that here. Do you know why? Well,
Slope is not constant.
because this is not constant. The slope is not constant. The time interval is going to be changing. And so it depends on where we are. You know, the slope is continually changing. Slope is changing. It's not fixed. If the slope were fixed over the entire time interval, then this slope is valid for that time interval. But this slope is only valid at a single time. Because in the next instant of time, what happens to the slope changes. And so that means that slope is no longer valid. Well, that's going to be a problem. And so if the slope is always changing, how are we going to figure out how long it's going to take? Because, you know, it depends, because here it takes a very short time, but over here it takes a very long time for the exact same concentration change. And so how do we handle this problem? So if I want to know, you know, what is the concentration way out here at this time, then how am I going to calculate that? Because I don't, you know, this continually changing. Or if I want, you know, if I want to know, okay, it takes this much time to lose this much here. Well, it's going to take a little longer here, and it's going to take a heck of a lot longer down here. And so, you know, how can I figure that out? Well, there are different ways, you know, I could figure it out, but probably the easiest way is, no, not the area under the graph, but probably the easiest way is to use some calculus, right? If we use some calculus, we could figure it out, but, you know, we don't have to use any calculus. What we're going to do is we're just going to get the equations that we get from calculus and use those to do this. And so when we have a problem like this, then what we do is we can do some calculus, because this is going to give this. We're going to get an equation that looks like this. You know, the instantaneous rate, or the slope at the tangent, is going to equal K times the concentration here. And then there's something called integration in calculus, but we aren't going to do that. And then the result from that is going to be what we're going to call the integrated rate law. And so this is the rate equation, or the rate law, which is just, you know, the rate law is just a mathematical equation that describes that curve, right, in one way. It doesn't completely describe the curve. you know, and laws are just these mathematical equations that describe these observations. And so we get this integrated rate law, and then we get it into a form that we like. And so the form that we like for this is the Lm of the concentration at time t over the concentration at time 0 is going to equal k times t, where t is or delta t, where t initial is time 0. Okay. And so by using this equation describes this curve, right, here. And so by using this equation, we can figure out the concentration at any time, or we can figure out the time interval it takes to get from one concentration to the next concentration using calculus. And so what you want to do when you're collecting your data is you want to look, because does it fall into one of, you know, these familiar patterns, like a constant rate, a first order rate. A first order rate, each time we cut the concentration in half, the time is the same. It's easier than looking at the slope, because each time we cut the concentration in half, the slope gets cut in half, but it's hard to eyeball that, right? Here, this is, you know, this is what happens when each time we cut the concentration in half in linear. Do you know this? Everybody knows y equals mx plus b, but tell me, what happens when we cut the concentration in half? How long does it take? Yeah, each successive time. And the answer is the half-life actually gets cut in half each time. So if we have the first half-life here, the second half-life takes half as long as the first. And so each successive half-life takes half as long. And so it gets smaller and smaller and smaller, and eventually, boom, it hits 0, right? And so these are the ways we try to describe. We try to understand these patterns in different ways so that we can describe them in different ways and figure different things out from them. And so there's one more pattern that's easy, or fairly easy to see. It's hard to see in terms of what's happening here, because if we look at the rate or the slope, you know, we look at the slope, which is equal to delta concentration over delta t, or, you know, actually it should be, because we're looking at the instantaneous, and so let's get rid of that and write this, you know, where the delta is very, very small. And so this is going to equal k, and this is going to be what we call second order dependence. A second order dependence means if we double the concentration, the rate or the slope increases fourfold, right? It's a squared dependent. That means if we cut the concentration in half, what happens to the slope? Well, the slope gets cut by a quarter. And so here we have a steep descent, and here it's just going to be a quarter of that. And then if we cut it again in half, it's a quarter. And each successive time we cut it in half, oops. Actually, it's going to spread out more. Be like this. Cut it in half. So it'll be like this. And so it's going to look like a curve like this. It's not going to be linear. It's going to be curved. But it's hard to eyeball the slope, right? Because here we draw the tangent line. This is the instantaneous slope at this time. Yeah, it's hard to see that. It's easier to see like this. The easiest way to see this is if we cut the concentration in half, it takes a time interval we call t1 half, or the half-life. The next one takes twice as long. And so this would be 2 times the original t1 half. And then the next one would be double that one. And so it just keeps getting longer and longer and longer, right? Twice as long each successive time. And so this one's going to take even longer to react, much longer. But we want to figure out, how long. And since the slope is always changing, this is continuously changing. We need calculus to figure out anything dealing with concentration changes or time changes, right? Because it's not constant. And so what we'll do is we'll do some calculus and integration, and we come up with this. The equation that describes this one is going to be called the integrated rate law. The integrated rate law, that again just comes from calculus. But the integrated rate law, in the easiest form for us to use, is 1 over the concentration at time t is equal to kt. Actually, I made a mistake with that one, but I'll fix it right now. 1 over A times concentration at time 0. This is a plus. I'm sorry, this should be a minus kt here. I think. Well, you don't have to derive these equations. We're just going to use them. All right, and so this will allow us to figure out the concentrations at different times or whatever. And so this is just the mathematics of the equations here. Okay, and so all we're going to do is we're going to collect the data, see what the curve looks like, and see, does it fit one of these, or maybe it's some other pattern. It could be some other pattern, you know. But if it's some other pattern, we aren't going to do the math for it because this is too much as is. This is enough, okay? And we'll leave it there. All right, so we're going to take a break, and then we'll check out the equipment, and then we'll set it up together. Okay.